Just returning to another idea that we have seen, this idea of related rates of change, where sometimes we have to use more than one rate of change to solve the problem. Basically it's using, well, call it whatever you like, the chain rule, implicit differentiation, rates of change, it's all the same thing, it's all our derivative there, but that idea that we could find dy dt by actually finding dy dx and multiplying that by dx to t. Let's look at some old HSC questions. Stones dropped into a pond, it creates a circular ripple. The radius of the ripple increases from 0, obviously, because the stone's not there yet, but then at a constant rate of 5 centimeters per second, the radius of this ripple comes out. So what rate is the area enclosed within the ripple increasing when the radius is 15 centimeters? Okay. So in other words, we want to find dA dt. That's what we're trying to find. They've given me dr dt, the rate of change of the radius. So to link these two things together, ideally I would like dA dr, some sort of expression for dA dr, because then the dr's, if you like, cancel and you would get dA dt. Okay, well we have a formula for the area of a circle, pi r squared. I can differentiate that, dA dr is 2 pi r. So I now can put that together and create a formula. So 5 times 2 pi r, 10 pi r. Our question was when the radius is 15 centimeters. So when r is 15, we get 150 pi. We have our answer. The units for that, because it's area with respect to time, would be centimeters squared per second. Ferris wheel, radius 20 meters, rotating at a rate of 1.5 radians per minute. Remember, whenever we're using calculus with trig, radians is the measure we need to use to make it work. So they were nice to us and actually gave us the rate in radians per minute rather than degrees per minute, so we should be okay. The angle of elevation at the top of the carriage is theta. Okay, and they've got that in our diagram. First thing I want us to do is to show simply that dh to theta is 20 cos theta. So we need to get a relationship between h and theta, which, well, we've got a triangle here. We can see h over 20 is the sine of theta. So h is 20 sine theta, differentiate that, 20 cos theta. Okay, so we've got the first bit. At what speed, so not velocity, but speed, is the top of the carriage rising when it's 15 meters higher than the horizontal diameter of the Ferris wheel? We're trying to find dh to t. We just found dh to theta. So ideally right now I'd like to link theta and t if I can. Well, they did tell us that. They told us to theta to t, the rate of change of the radians with respect to time. So that's 1.5, I've written it as a fraction 3 on 2. So okay, dh to t, I can combine these two together and get a formula. Combine them together, I get 30 cos theta. They want when it's 15 meters high. The variable I've got is theta, so I'm going to have to work that out. When h is 15, if I look at that triangle, I can do some Pythagoras, that's root 175. So cosine theta, I can read off that is the root of 175 over 20, times it by 30 in our formula, we get 19.843. So there we go, we're rising at a rate of 19.8 meters per second. Distance A is inversely proportional to distance B, such that A is 9 over B. Okay, and they're both in meters. Two distance vary with respect to time. Distance B increasing at a rate of 0.2 meters per second. What is the rate of change of A when A is 12? Okay, we want to find dA to t. We've been given dB to t. I've been given a relationship between A and B. I should be able to find the link between these two of dA to B. I think that's the one we need to find. The A is 9 over B, so dA to T will be minus 9 on B squared, because dA to B would be minus 9 on B squared. Now when A is 12, B is 9 on 12. Subbing all that information in, we get minus 16 on 5. Okay, so we have our rate decreasing at a rate of 3.2 meters per second. Woo, that'll do us.